utility session introduced me from Tohoku University. And the first talk in this section is efficient lookup-table protocol in secure multiparty computation. And don't release in the talk.
Thanks. So this talk is about what happens when a language and a systems perspective comes to bear on the problem that takes place in the cryptography world. The goal that we're looking for in this world of cryptography is that we want to be able to have encrypted values and do computation on encrypted values and have those essentially simulate the effect of doing computation as if it was an unencrypted value. And so that's setting up a homomorphism between the space of unencrypted values and the space of encrypted values. And there was a big breakthrough a few years ago. Craig Gentry, back in 2009, showed for the first time ever that it was possible to do what was called fully homomorphic encryption. But that's hugely inexpensive, like 10 to 100 trillion times more costly to do computation than it is straightforward. And you're using huge crypto words. You use 1 million bits to encode 1 bit. There's a more efficient version, a more efficient means of doing something rather similar, and that's where we've been exploring the idea of secure multi-party computation. And now you have the notion that we're going to encrypt something by spreading its value, smearing its value over multiple servers. And so in each of the servers, you're actually going to get just as actual junk, but it's only when they come together that they actually have meaning. But let me talk a little bit about this idea of homomorphism. It's been known for a long time that different cryptographic protocols might have homomorphic properties. RSA is something that gets used all the time. Its encryption is just exponentiation modulus some particular number. And if we define a notion of the multiplication on the encrypted side, I'm sorry, I have an error on the bottom right, that should be EK of Z. If we do the multiplication on the right-hand side just by multiplying the crypto words and doing it in modulus, then what we discover is that there's a homomorphic property. So you can get RSA respecting multiplication, you just can't get it respecting addition. And it was thought for a long time that you can't get systems that would do both. But at the same time, as I say, there's been this notion of secure multi-party computation where you actually have values spread around in different parts. And so I'm going to talk about the version of this called shared computation, or arithmetic sharing. And the idea here is that we're going to share a value across multiple servers. In this case, we'll take 3 servers. And the way that we'll do it is we'll pick x1 and x2 completely randomly, and then x3 will be the original value x minus those other 2, mod 2 to the n. N might be something like 32. We might be dealing with 32-bit numbers. And because they're drawn from random distributions, even x3, which is computed, it's computed with respect to randomness, and so it's also completely random. And from any one of x1, x2, or x3, you get 0 information about your actual value. In fact, from any 2 of those, x1, x2, or x3, you get 0 information about your actual value. And so the goal is then in this shared computation is with these values that are by themselves providing no information at all as to what the real value is, the real value x, we're going to do computation on the real values by performing computation on these shares of the values. So how would we do that? And by the way, this is all background at this point. I'm just giving you a sense of the background. So we do it by, with addition. If you've got a share of x's and a share of y's, you can just locally add the shares and you're done. It's just completely local. If you're doing product, you've got x1 plus x2 plus x3 and y1 plus y2 plus y3. And if you imagine multiplying those together, you get all the cross terms. And so in order to be able to compute a share of one thing, we need to be able to communicate some of the values around. And so maybe the value that we compute on B will be this one shown in the yellow, that sort of L-shaped thing, and we construct the other L-shaped things accordingly. So with a single cyclic communication, what we're able to do is compute shares of the product and keep the thing moving. So what we did was we built a simple eDSL in Haskell to describe this. as a sort of foundation of our work. And the intent is we write monadic code, and that monadic code gets executed on the same code gets executed on the 3 servers, and we built it all nicely with type classes so that we could introduce shares of new data types and things like that. Addition is all done locally, as we saw, but multiplication, or if you generalize, if you think about just 1-bit things, that's just AND, the AND operation, it requires 1 cyclic communication. You could do a whole bunch of those in one go, and so you could do it like a parallel and still with a vector of values, of bits, you could still do it with just 1 cyclic communication. And there's a little twist that you need to get right here, in that when you're sharing this information around, the risk is that you're sharing information, so you actually have to add entropy before you do that sharing of information, so that you know that you're not actually leaking any information in the process. So that's a little bit of resharing and randomization that you have to do before you send the values around. But once you set this up, then you've set the scale for doing shared computation. And now the question is, how do we start building things on top of these kinds of ideas that have been known for a long time? How do you build interesting applications? And then how do you start engineering those applications to find out how to make them work well? So one of the example applications that we looked at was this notion of filtering data. You might be moving data, say, from your corporate network to the public network, and what you wanted to do in the process of moving that data across is that you might want to align some information from the documents. And it may be that you want to remove suppliers' names or prices or things like that. You may have a set of rules that describe what kind of information has to be removed before you move it into the public space. Now, if we twist it slightly to say that I'm actually not putting it in the public space, but I'm sending it from me to you, from my private space to your private space, and there's still some information that I want to make sure I don't leak to you, but the whole thing I don't want to leak outside of the, either you or me. And so one of the challenges is I certainly don't want to be doing it on unencrypted files. I want to have the files encrypted. So imagine I do them encrypted in some way, and then if I could do that computation still working on the encrypted files, that means that if somebody has got into one of the servers on the way, they can't read the data just by eavesdropping on the content of the server. So the idea is, how do I push this through so that the whole thing works on encrypted values? Well, there's another twist that happens. I've shown it here that it might be encrypted with some scheme, whether it's a fully homomorphic encryption scheme or something like that. But my data probably doesn't start out encrypted in a scheme which has this nice homomorphic property about it. It probably starts out in something much more like AES. Maybe it's sitting on my server, encrypted with AES. I want now to move it into this scheme where I can do computation, do the computation, and then move it back into a scheme, into an AES scheme. And through that whole thing, I never want it to be in plain text. Okay, so it has to be under some sort of encryption at every stage of that process. So in particular, if we were to cast this into something like the share computation, it starts to look a little bit complicated. We start out with a document in AES, and we maybe split it off to 3 separate servers in that random, in that way that I showed you, the x1 plus x2 plus x3, if you think of that plus as being XOR. I may have a key on, maybe I have it on my local iPhone, which I also send to these servers. And now I do the AES decryption in this shared setting. So I'm doing decryption, but in such a way that the plain text never actually exists on any of these servers, only a share of the plain text. That is, a value which by itself is completely random and gives no information whatsoever about what the plain text is. And then in that shared setting I can do my filter operation, and then in that shared setting I can do my re-encryption, and I end up with an AES in the target space. So one way that you can think about this kind of transformation is to use something a bit like a commuting diagram, where along the bottom of this is the idea of, in the share world, I could take a document, I could apply my filter, and I get a new document still in my share world. But if I start up in the AES world, what I could do is, first of all, encrypt it with the share thing. So I'm now in the share world of the AES world, and then inside the share world, I could decrypt the AES, sort of like a functorial application of decryption, and then do the reverse the other way around. What's cool about doing this is that it's a natural way then to, as it were, give us the homomorphic property that we're looking for on something like AES. It's, as it were, lifted up the homomorphic property from an underlying scheme to a homomorphic property of AES. So the question then is, how well can you do AES? Well, when we started, the fastest speed that was known for doing AES in any of these schemes, well, there was one that took about 2 seconds per block. Then we discovered one that would do 6 blocks in a second. That's a block of AES is 128 bits. Do 6 of those in a second, and that was quite cool. So the question is, could we do any better? Could we improve the performance by again bringing language and system kind of techniques to bear on making this work better? So, give you just a quick sense of AES. AES starts out with the plain text coming in, and then you mix in some key material, and then you do all sorts of stretching and pulling of the stuff, and you go around that inner loop 10 times, and then you come out at the bottom and you do a little bit more to finish it off. And most of it is straightforward from the point of view of doing shared computation, because most of it is XOR or moving stuff around, and that will be no problem at all. Moving encrypted values around is just the same as moving regular values around. That kind of motion is polymorphic. The key part, though, is lookup tables. So what we're going to have is a whole bunch of lookup tables where I've got, let's say, a byte as an index and 256 elements, and I want to look up that byte in that table. But the trouble is, I don't have that byte. If I'm on one of those servers, I have a random sequence of bits, and I want to look it up in the table. And on another server, I have a random sequence of bits. And on another one, I have a random sequence of bits with the property, global property, that if I were to XOR them all together, that would be the index. So the question is, how do you get a table lookup to work, and how do you get it to work efficiently? So the factorization of it that we came up with is that it's really, you can break it down to, first of all, just doing a Demux. Imagine that you're doing it for the real thing, first of all, of taking the 8 bits and expressing it as 256 bits, all of them 0, and then just one of them being 1. And then what we'll do is do an AND of that with the table itself, and then you can do an XOR of the whole of the result, like an inner product. And so only the one where you had the 1 would come through, and it would add up. And this generalizes nicely to the setting of the share, because at this point, what you can do is it distributes nicely with the XOR, which is the share function of the property. So we took this and we said, how do you now express Demux so that we can do Demux really efficiently? So Demux is expressible as a divide and conquer. So there's a specification of it, and the divide and conquer you can also express as a parallel product in quite a cool way. So here's a little example at the top. If you demux the value 1, and I'm going to count from the left 0, 1, 2, 3, and on this one I'm going to demux 2, count from the top 0, 1, 2, 3, and if I take the Cartesian product of that, and start counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's the Demux of 9. So that's the divide and conquer of Demux. I can also express it as taking that thing at the bottom and expanding each bit 4 times. So I get 0, 0, 0, 0, and then again zeros, and then the 1s, and then the zeros, and then the one across the top, I'll replicate it 4 times, and then I can do a parallel AND. And so if you do this a bit more and a bit more and a bit more, you get a circuit that looks a bit like this, which almost looks like a kind of hardware circuit, but we're going to try and build circuits like this to operate on these shares of values. So this will work beautifully, just in the plane. But what's nice about this one is it also factors with regards to XOR, and so we can do the share version of it. So when we look at constructing this kind of thing, of using this kind of thing in the code for AES, we now have our AES code, which looks actually remarkably similar to the plain Haskell AES code, except we monadified it. And there's just a couple of places where we do operations which are table lookups. So the indexing function is the place which is built on top of this idea of table lookup. And that's the time where we're going to do this big operation. Now from this diagram, each time we do an indexing, there's 3 global multiplies that we have to do to accomplish it. So that's 3 network operations. And so when we're doing this for each round, we're doing 3 multiplications on a round because we're doing all 16 elements of the state at the same time in parallel. And so that gets us 33 multiplications. So that already was a big win. We could do AES with just 33 communications. And there's a bunch of other kinds of optimizations we did. This whole computation has the notion of do some compute and now do a network operation where you sit around and you wait, and now do some computation, and now do a network operation, and so on. We're on a fast network, and so we wanted to grow the amount of computation a bit in order to figure out how to take advantage of the most computation, and then we also interleaved a couple of threads, and so we measured to see what's the right balance of thread and computation in order to get the optimal. So we were quite pleased with the results, 320 AES blocks a second. That was quite an improvement from 6. And so it means now that you can run AES in this kind of setting fast enough to do real-time voice applications. So our conclusion from exploring these kinds of applications is that this embedded DSL in Haskell was providing us a really flexible platform for exploring the kinds of programs and algorithms that arise in this really kind of strange architecture where even just doing a multiply is a network operation and really quite expensive. And what was exciting also, just from a pure research point of view, was that it indicated that the same kind of way that we do table lookup applies even in something like FHE, now that they've figured out how also to do these kind of bulk, parallel, and kinds of operations together. And with that, I'll take any questions.